Let's take a look at our constant acceleration math model. This is the complete math model, and we're going to start by reminding you of what acceleration is. So we have this equation, a equals delta v delta t. That you could think of that one as like the definition of acceleration, right? It's a ratio of how much my velocity changes relative to how over the amount of time I take to experience that change in velocity. And as a reminder, the deltas are really a final minus initial. I'm not going to write final minus initial over and over again. I'm just going to keep delta t over at the bottom. Remember that delta t can often be replaced, or it can be written as just t. But whichever version you choose, it always represents a time interval between some initial time and some final time. We keep things kind of simple by saying, let's make our initial time 0. And if we do that, then this guy goes away. So imagine this guy going away. And then whatever our final time is they're all the same value. Okay? But to be really complete and to handle the broadest situations, we always think of t or delta t as really a time interval. You also met this equation already, so we actually have an equation for position. Sometimes you might just write x or x as a function of t. Okay, if you do that, you're really saying it's a function of a time interval, because t is a time interval. But if you keep the f and I, which I think is probably the one where it's safe to use. The reason I like using f there is it reminds us that that's the x sub f is x at t sub f. So if you're putting in your final time, wherever you are at that time, that's what x sub f is. X sub I is your position at t sub I. So if you have t sub f and t sub I, in other words, this is not, if this is non-zero, right, then you're always plugging in, you got to look at that time interval when you plug that value in for t. You got to take the interval between these two and plug that in for t, because t is delta t. Okay? Now if time is 0, if initial time is 0, then as I said earlier, all these mean the same thing, and that's why that's your position at time t, okay, where your initial time is 0. But again, I'm going to keep this there to remind you that this t up here is a time interval. And of course, your initial velocity is your velocity at that initial time. We're going to generate 2 more equations. They're not really, these are really the equations, frankly. But this is often written in another way. And what we do is we just do some algebra. That's it. We just rearrange this equation because sometimes it's easier, just by a matter of convenience, we like to express a thing by itself on the left equals stuff. Okay? This acceleration equals stuff. But sometimes, if we have, remember what the characteristics are of motion, right? It's where you are, position, how much your position is changing with respect to time or velocity, and then, of course, acceleration. So acceleration is in here, and our accelerations are always constant, over a given time interval. But we also typically can use this equation. Okay? This is nothing more than this thing rearranged. So real quickly, remember delta t and t mean the same thing as symbols. So I have a equals this thing over t. I multiply a times t. That's where this term comes from. Then I add vi to both sides to get rid to separate vf and vi. If you do that, you get this. Okay? So the equivalent of these equations are in the book. Which ones? This one, this one, and this one. These sufficiently, and you can even argue it's just these two, these sufficiently describe constant acceleration. Okay? Definition of acceleration, how fast, where I am after I accelerate, even if I'm already moving at the beginning. And this is how fast I'm going if I accelerate after a certain amount of time, even if I'm already moving at the beginning. Now there's two more equations, and these are basically factoids. This class is not about deriving equations over and over again. We shall stand on the shoulders of giants, and what we do is we take these two equations and we throw them into an algebra mixer. That's not a technical term. Algebra magic. All right, we throw, or an algebra blender maybe. And what we do is we take these two equations and we notice they both have t. And what we do is we we basically try to get rid of t. I have two equations, they both have t in it. That means, for example, I could rearrange this so that I could say, well, t is just equal to what? Change in velocity divided by acceleration. So if I do that, and then I could take this whole thing and put it in here, that would get rid of the t's. Okay? The good news is you don't have to prove, that's been done a long time ago, and the results don't change if we do that. And it turns out we get another equation that comes in handy. Remember, what did I do? I substituted for t, right? Where I turned this into a t equals equation, then I took t equals stuff, and I took that stuff and I substituted in for t, and I try to simplify, and you get something really interesting. You get an equation that looks like this. My final velocity squared is just my initial velocity squared plus 2 times my acceleration times delta x. So this equation is also in our course, it's in the book. And you might go, yeah, good question is, gee, Mr. Cacchino, that's really interesting. Why the heck do that? I mean, like I said, this isn't new in terms of like a new phenomenon. It's really just playing with these two equations. So why is this handy? Well, notice the cool thing with this is it doesn't require any time information, or it doesn't try to factor in time at all. So I refer to it as the timeless equation. So it comes in handy if you don't have any time information. You might have a physical system where you know 1, 2, 3, 4. You know 3 out of the 4 things here, and you're interested in the 4th one. And none of those things has any time information. It's not time. So that's one. You want to know that one. The other one is we go back to our idea of average velocity. Because when we accelerate, remember what happens when you accelerate. Your velocity changes. So now we have an initial velocity. So we're going to look at a velocity time graph. And we're going to accelerate to a final velocity. Right? Now, if we do that, we can figure out how far we've gone. Or we can represent how far we've gone. How? By the area. So this is delta x. This is our delta t. Okay? Now, we remember average velocity. So even though I accelerate, my position changes quadratically, right? So we know that this velocity time graph is going to correspond to a position time graph that's curved. So my delta x on something like this is how much my position has changed. There's delta x, right? How much my position has changed, and here's delta t. Okay, well, if I have any kind of delta x information and delta t, I still have an average velocity. This doesn't go away. I could talk about an initial velocity, final velocity. Those are instantaneous. Any velocity along this line is an instantaneous velocity at whatever time I'm looking at, because it's there at that instant. It's that value at that instant. That's what the blue line tells me. But I also can talk about my average velocity for this journey. That's just going to be delta x over delta t. Well, it turns out that if you look at your average velocity and you have this situation where, and here's the big caveat, what's our boundary condition? Constant acceleration. So the blue line has a constant acceleration of a. As long as that's met, if that condition's met, it turns out, a little algebra, actually less algebra magic than this, it turns out that that's also equal to 1/2 times my initial velocity plus my final velocity. So we have another equation for average velocity when I'm experiencing a constant acceleration. It's just this. So the handy thing to remember, and you might not be used to seeing two equal signs, one after another. That they literally mean equal equal, right? So I might say V average is equal to this, or maybe I'm not interested in delta x, delta t, so I kind of ignore it, or I don't use it, and V average is also equal to this. Or if I know my final and initial velocities, this equation, it doesn't look quite like a typical equation because you've got math on the left, math on the right. So it looks like two operations equal each other. But this is basically an equation with what? 1, 2, 3, 4 variables. So when you're trying to pick equations and you're trying to decide which one to use, the one you use depends on what you know. So if you're trying to find delta x and you have time, initial velocity, final velocity, you can use this. Any combination of those, right? If you know 3 out of the 4, you can solve for the fourth one. So this is our constant acceleration math model.